Good day to all of you. So we're already in chapter 9, main memory. Actually, this is the first topic for the part of memory management. So to know more about main memory, so let's start our lesson. So again, chapter 9 is all about main memory. So the contents of this chapter for memory management is we have background, contiguous memory allocation, paging, structure of the page table, swapping. So we have an example, the Intel 32 and 64-bit architectures. And another example, we have the ARM V8, ARM version 8 architecture. So the objectives are the following. So to provide a detailed description of various ways of organizing memory hardware, to discuss various memory management techniques, and to provide a detailed description of the Intel Pentium, which supports both pure segmentation and segmentation with paging. So for the background, so program must be brought from the disk into memory and placed within a process for it to be run. So any programs that you'll be using, for example, using in a computer, it should be loaded into memory. So main memory and registers are only storage CPU that can be accessed directly. So memory unit only sees a stream of addresses plus read requests or address plus data and write requests. So register access is done in one CPU clock or less. Then main memory can take many cycles causing a stall. So why does the main memory causes a stall? Because of course, in comparison with the speed of CPU and main memory, CPU is relatively faster than main memory. So the logic is like this. For example, if you have two people who are working together, then employee A finishes his or her task faster than employee B, then his finished task will be passed to employee B. So if employee B is slower, so it means that the tasks that are done by employee A will pile up to employee B. So that is why. So in a real world application or for computer application, so one solution to make your system faster is you have to add additional RAM or random access memory in your computer. So next is we have cache sits between main memory and CPU registers, and then protection of memory required to ensure correct operation. So this mentioned protection, so need to ensure that a process can access only those addresses in its address space. So we can provide this protection by using a pair of base and limit registers. This define the logical address space of a process. So for example, we have this in the memory. So from this is we have this is where the operating system is located in memory. So for example, we have three processes here. So for this process, so this 300040, it's base um, address, and then we have 420940, it's the base plus limit. So it means that the address here that the base and limit registers defined for that process is the logical address space of a process inside main memory. So next is we have the hardware address protection. So CPU must check every memory access generated in user mode to be sure it is between the base and limit for that user. So for example, so the CPU, so it will generate an address. So if it is greater than or equal to base, so it will continue to add the base plus limit. Okay, so let's go first with this one. So if the CPU that is produced or derived by the address derived by the CPU is what? If it is less than the base, so there is a trap to operating system, which is illegal addressing error because the address derived by the CPU is less than the base. But if it's greater than or equal to the base that is produced, so it will continue to add the base plus the limit if it is less than with the limit. So if it's greater than the limit, so again, this will have a trapped operating system illegal addressing error. So for it to be loaded to memory, the address should be greater than or equal than the base and less than the uh, base plus limit. So it will be loaded into memory. So the instructions to loading the base and limit registers are privileged. So next is we have the address binding. So programs on disk ready to be brought into memory to execute form an input queue. So without support must be loaded into address 0000. Okay, it's inconvenient to have first user process physical address always at 00. How can it not be? Because for the addressing of main memory, it's not always the same address. The address can be, it's not a really random. At least the free space in memory will be its address. So addresses represented in different ways at different stages of a program's life. So source code addresses usually symbolic. Compiled code addresses bind to relocatable addresses such as 14 bytes from beginning of this module. And then linker or loader will bind relocatable addresses to absolute addresses, so such as 74014. And then each binding maps one address space to another. So next is binding of instructions and data to memory. So address binding of instructions and data to memory addresses can happen at three different stages. So we have compile time. If memory location known a priori, absolute code can be generated. Must recompile code if starting location changes. So what is absolute code? So this code with bindings to absolute memory addresses. So next is we have load time. Must generate relocatable code if memory location is not known at compile time. So relocatable code, code with bindings to memory address that are changed at loading time to reflect where the code is located in main memory. So next is we have execution time. Binding delayed until runtime if the process can be moved during its execution from one memory segment to another. So need hardware support for address maps such as base and limit registers. Okay, as you can already see, this is already shown in the previous lessons in operating systems. So again, our source program, so it will be compiled by the compiler or the assembler. So it is called compile time, the amount of time it took for the source program to be compiled or assembled. And then its product of the compiler or assembler is the object module. And then it will be combined to other object modules. And there is a linkage editor, and then it will be the product of the linkage editor will be the load module, and a load module will be combined with the system library, and then it will be loaded in, of course, the loader. So from the linkage editor, the amount of time from the linkage editor to loader, that is the load time. And then for the loader, so from here with in-memory binary memory image, so it will be combined with dynamically loaded system library. So at that will be the execution or runtime. So it uses dynamic linking for dynamically loaded system library. So next is we have logical versus physical address space. So the concept of a logical address space that is bound to a separate physical address space is central to proper memory management. So logical address generated by the CPU, also referred to as virtual address, and the physical address, address seen by the memory unit. So for you to understand the logical and physical address in a real-world scenario or analogy, think of physical address. For example, your home, the house. Okay, the physical address is the land where your house is located. The actual land, okay? So that will be the physical address. How about the logical address? The logical address is the address. For example, if you ordered something online, and online company or the logistics is asking for your address for it to deliver at your home. So that address that is indicated in the, of course, in the address, that is the logical address. So that's the difference between logical address and physical address. Again, physical address, for example, in our house or in our homes, the actual land where our home is situated, and the logical address is the, of course, the assigned house number, and then what barangay you're in, what province you're in. So actually, logical address can change. What if, for example, your barangay has a very prominent figure or persons, and then after a long time, it can be changed, the name of the barangay with the name of that prominent person. So that is all, that is possible. So logical address can change. Physical address can change also if, for example, your home, you will really going to change your location or bring your house to another location. So that's the change of the physical and logical addresses. So logical and physical addresses are the same in compile time and load time address binding schemes. The logical or virtual and physical addresses differ in execution time address binding scheme. So logical address space is the set of all logical addresses generated by a program, and physical address space is the set of all physical addresses generated by a program. So next is we have the memory management unit, or the MMU. So hardware device that at runtime maps virtual to physical address. So the CPU produces a logical address, and then of course this memory management unit maps the virtual to physical address. It's its responsibility. So it will have its physical address, and it will be this physical address will be put for where, for example, the data will be put in the physical memory. So many methods possible covered in the rest of this chapter. So consider simple scheme, which is a generalization of the base register scheme. So the base register now is called a relocation register. So relocation register, it is a CPU register whose value is added to every logical address to create a physical address. So for primitive memory management. So the value in the relocation register is added to every address generated by a user process at the time it is sent to memory. And then the user program deals with logical addresses. It never sees the real physical addresses. So execution time binding occurs when reference is made to location in memory and logical address bound to physical addresses. So we have this illustration of the using a relocation register. So for example, the CPU has a logical address of 346, so greater than or less than, so it will be scrutinized by the memory management unit to map the physical address. So the relocation address at this time is we have 14000. So what we're going to do of the memory management unit, it's, so the logical address is 346. It will just add the value of the relocation register. We have 14000, and then so we have 14346, and this will be the actual physical address in memory. So that is how the memory management unit maps the logical address from the CPU, and then corresponding to its physical address in the main memory. So next is we have dynamic loading. So the entire program does not need to be in memory to execute. So that's a good thing, because not, for example, what if your program is too big? For it to execute, it only needs parts of the program. So routine is not loaded until it is called. So better memory space utilization. Unused routine is never loaded. All routines kept on disk in relocatable load format. So useful when large amounts of codes are needed to handle infrequently occurring cases. So no special support from the operating system is required. So implemented through program design, And OS can help by providing libraries to implement dynamic loading. So next is we have dynamic linking. So we have this term, static linking, system libraries and program code combined by the loader into the binary program image. And then if we have the static linking, we also have dynamic linking, linking postponed until execution time. So a small piece of code or stub used to locate the appropriate memory resident library routine. So the stub replaces itself with the address of the routine and executes the routine. And then the operating system checks if routine is in the process's memory address. So if not in address space, add to address space. Dynamic linking is particularly useful for libraries. So system, also known as the shared libraries for dynamic linking libraries. And then consider applicability to patching system libraries. So versioning may be needed. Okay, next is we have the contiguous allocation. So main memory must support both OS and user processes. So of course, limited resource must allocate efficiently because our memory is there is a fixed amount or a fixed capacity of main memory. So it should be allocate the data or the programs that which will be using the space for the main memory must be allocated efficiently. And then contiguous allocation is one early method. So main memory usually into two partitions. We have the resident operating system, usually held in low memory with interrupt vector. And the next user processes then held in high memory. So each process contained in single contiguous section of memory. So meaning of contiguous is they are in one place. Okay, they are adjacent to each other. That is what is mean with contiguous allocation. So relocation registers used to protect user processes from each other and from changing operating system code and data. So base register contains value of smallest physical address. So that's why base plus limit address. And then limit register contains range of logical addresses. Each logical address must be less than the limit register. So as we already discussed in the previous slides, so base is the smallest physical address while the logical address must always be less than the limit register. So the MMU maps logical address dynamically, can then allow actions such as kernel code being transient and kernel changing size. So kernel being transient means it's temporary. So because kernel change its size over time. Okay, next is we have an illustration of hardware support for relocation and limit registers. So again, this is using relocation registers. So the CPU will have or produce logical address. So if it's greater than the limit register, so it will have a trap, an addressing error. But if the logical address is less than the limit register, then from the relocation register, it will add the value of relocation register in the logical address, and it will produce a physical address which corresponds to the physical address in the memory. Okay, next is we have variable partition. So multiple partition allocation. So degree of multi-programming limited by number of partitions. Variable partition sizes for efficiency. Size to a given process needs. So what is a hole? Block of available memory. Holes of various sizes are scattered throughout memory. So this is a hole, this is a hole, so these are holes. When a process arrives, it is allocated memory from a hole large enough to accommodate it. Process exiting frees its partition, adjacent free partitions combined. So adjacent, so this will be combined to have a free memory space. And then operating system maintains information about the allocated partitions. And then we also have free partitions, which are the holes. For example, so we have this for memory, we have three processes, 5, 8, and 2. And then, of course, fixed memory location for OS. What if process 8 has already finished its execution? So it will be swapped out from the memory. So the space that process 8 leaves, that will be the whole. And then what if next is process will be executed, so it will be loaded in memory. So this will be put on the whole, as we can see, but of course there's still additional, or well, still a hole here, a space. And then what if process 5 has finished its execution? So we have, it will leave again another hole in which the process 5 has left. So we have two holes here. So that is the, what is the meaning is, there is always have a pre-partitions, or hole after each processes finished its execution. So for example, what if process 9 has finished first and then process 5 is still here? So this, for example, this will be a hole. So it is said here that adjacent free partitions will be combined. For this, it cannot be combined because we have still process 9 here that is executing. Once process 9 will be finished, so the three holes will be combined since they are adjacent free partitions. Okay, next is we have the dynamic storage allocation problem. So how to satisfy a request of size n from a list of free holes. So we have three suggestions. So we have first fit, allocate the first hole that is big enough. And then we also have the best fit, allocate the smallest hole that is big enough, must search entire list unless ordered by size, and then produces the smallest leftover hole. And then we also have the worst fit, allocate the largest hole, must also search the entire list. It produces the largest leftover hole. So first fit and best fit better than worst fit in terms of speed and storage utilization. So for example, let's have an example here. Okay, for example, this is our memory. Okay, example. Let me, allow me to draw. Okay. Example, this is already being occupied. And then for example, we have, for example, just for example, 8 MB. Just for our example. We have 8 MB. We have 6 MB. Okay, sorry for the handwriting. And then we have 10 megabyte free space, for example. And then, for example, we have a chunk. For example, this is 5 MB. Okay. So, let's have an example. Assuming our block here is equally, it's a square, okay? So, I'm sorry for my good drawing. Okay, first is we have, let's use the best fit, first fit, best fit, and worst fit. For example, 5 MB. If we're going to use first fit, where it will be, where will our 5 MBB process be located or be situated? If you're talking about first fit again, allocate the first hole that is big enough. Since 5 MB, it will first encounter 8 MB. So since this is the first hole that is big enough for 5 MB, so 5 MB will be put inside this space for which is 8 megabytes for first fit. Okay? Next, if best fit, so allocate the smallest hole that is big enough, must search entire list unless ordered by size. Since this is not ordered by size, so it will check all the holes that is available. So we have 8, 6, and 10. Which of them has the smallest leftover hole if 5 MB will be put inside that free partition? So actually, the best fit, using best fit, it will be 6 MB because if you're going to put it in 8 MB, you still have 3 megabytes leftover whole. For 6, it's only 1. And then for 10, we have 5. Okay? So for best fit, so 5 MB will be situated inside the 6 megabyte free partition. So last but not the least is we have the worst fit. So allocate the largest whole must also search the entire list. So just like best fit, it will check all the available free partitions. Then after that, of course, it will allocate the largest whole. So again, the leftover here is 3, this is 1, and this is 5. So since for worst fit, it will always allocate the largest whole. So this 5 MB for worst fit will be put inside the 10 megabyte free partition. So that is the difference between first fit, best fit, and worst fit. So is there a case that for this fit that it will choose the same the same free partition? Uh, for first fit and best fit, that's always possible. So what if, for example, 6 MB will be put here, and they, for example, they interchange the space. What if the location has changed? So first fit and best fit will have the same free partitions that they will choose from, because worst fit will always choose the largest hole that it will fit. It has the largest leftover hole if you're going to put the process inside. So this is an explanation of how to deal with the first fit, best fit, and worst fit for the dynamic storage allocation problem. Okay, next is we have fragmentation. So, external fragmentation, total memory space exists to satisfy a request, but it is not contiguous. And then we have internal fragmentation. Allocated memory may be slightly larger than requested memory. This size difference is memory internal to a partition but not being used. Okay, so let's have another example. Okay, so again, let me draw again a memory. Okay, let's assume that this is already occupied. Okay, for example, we have 4 MB, for example. Okay, and then I have another 4 MB free space or hole. Okay, what if your memory or the process that you have is we have an 8 MB. The size of your process is 8 MB. It needs 8 megabyte um, space. Okay. For external fragmentation, so this example is internal fragmentation. Why? Because if you're going to add 4 megabyte plus 4 megabyte is equal to 8 megabytes. But because since they are not adjacent to each other and there is this portion which is occupied by another process, so this is so called the internal fragmentation, because again the definition is total memory exists to satisfy a request exactly as 8 MB, but it's not contiguous. So still this 8 MB cannot be accommodated inside memory because the free space here are not contiguous. So what about internal fragmentation? So allocated memory may be slightly larger than requested memory. So this size difference is memory internal to a partition but not being used. So for example, we have 4 MB, and then we have we have a process that needs 3 MB. Okay? So actually 3 MB will fit 4 MB. Okay, this memory. This will fit. So but it will leave a hole, which is 1 megabyte. So actually, that one hole or 1 megabyte there is called already the internal fragmentation because the space here is 4 megabytes, but because the process that has arrived needs 3 megabytes, and then if you're going to put here and then there is still a space, so that 1 megabyte so is memory internal to a partition but not being used. So that is an example, that is what is so called the internal fragmentation. So first fit analysis reveals that given n blocks allocated 0.5, so for this, for first fit, 0.5 n blocks lost to fragmentation. So because of that, 1/3 may be unusable. So so it means that they have to use the 50% rule. So that's why it's 50%. We have 0.5 n blocks lost to fragmentation. Okay, what's the solution for that? So, reduce external fragmentation by compaction. So, shuffle memory contents to place all free memory together in one large block. So, compaction is possible only if relocation is dynamic and is done at execution time. So, we have the I/O problem. So, latch job in memory while it is involved in I/O. So, that is the problem with compaction. If the relocation is dynamic, because of course, for I/O, the address is fixed. So, do I/O only into OS buffers. So, that's the solution. So, now consider that backing store has some fragmentation, has the same, rather, fragmentation problems. So next is we have paging. So physical address space of a process can be non-contiguous. Process is allocated physical memory whenever the latter is available. So paging, this avoids external fragmentation, avoids problem of varying sized memory chunks. So divide physical memory into fixed size blocks called frames. So size is a power of 2 between 512 bytes and 16 megabytes. So also divide logical memory into blocks of same size called pages. And then keep track of all free frames. So to run a program of size n pages, need to find n free frames and load program. Then set up a page table to translate logical to physical addresses, and backing store likewise split into pages. And though it avoids external fragmentation, there still have an internal fragmentation for this setup. So we have the address translation scheme. So address generated by CPU is divided into, for using the paging, is we have the page number or P used as an index into a page table which contains base address of each page in physical memory. And then we also have this page offset or D combined with base address to define the physical memory address that is sent to the memory unit. So we have this page number and then page offset. So, for given logical address space 2 raised to m and page size of 2 raised to n. So, these addresses are powers of 2. Okay, so how does the paging hardware work? So, for example, the CPU's logical address will be composed of the page number and the page offset. So, as already indicated here. And then, the page number points to the page table, the corresponding values of for the logical address space. And then we have this offset will be added with the physical address. Once the value of page number is located in the page table. So for example, this is F. So our example here is F. Then combined with the physical, rather with the offset, page offset, and then this will be the physical address will be used so that it will be situated inside the main memory or in the physical memory. Okay, next is paging model of logical and physical memory. So we have logical memory, page 0, page 1, page 2, and page 3. And then we have a corresponding page table. So page 0 will be situated in physical memory frame number 1. So that's why it's here. So our page 0 is in frame number 1 because in the page table it is indicated here. So our page 1 will be located in frame number 4 of the physical memory. And then page 2 will be located in frame number 3 in the physical memory. And last but not the least, page number 3 will be situated in frame number 7 of physical memory. So that is the how does the paging model of logical and physical memory. Okay, next is we have paging example. So logical address is equals to 2 and M is equals to 4. So use a page size of 4 bytes and a physical memory of 32 bytes or 8 pages. Okay, so we have M is equal to, we have, the page size is 4 bytes. Okay, so we have our page table. Okay, since, for example, so our logical memory here is A, B, C, and D. So it will be located at 5. Since we have to multiply it by 4. So 5 times 4 will be equal to 20. So that's why our A, B, C, and D is located in number 20. Okay, next. This is our next data. Okay, so this will be located in 6 in the physical memory. So times 4, we have 24. So that's why this is located here. Then for I, J, K, and L, so this will be located in 1 times 4 is we have 4. So that's why we have here in the frame number of 4, page size is 4 bytes. Okay, so in total, this is the physical memory is equal to 32 bytes. And then last but not the least, our M and OP will be in page 2. So for the page table, 2 times 4 is we have 8. So that's why MNOP is here in the frame 8, 9, 10, 11. Okay. So this uses with bytes. So that's why it is larger compared with the other example. Okay, next is we have paging, calculating internal fragmentation. So we have page size is 2048 bytes and the process size is 72,766 bytes. So we have 35 pages plus 1086 pages. Okay, so let's access our calculator. Okay, so let's just see the computation. So, okay, our page size is 2048 bytes and process size. So, how many page will we need? So, we have 72,766. So, we have divided by 2048. So, that's why it's 35 pages. And this decimal part with the decimal point, this is the remainder, the 1086 bytes. So 1086 in the powers of 2, where it will be, where will it fit? Okay, so we have, it will fit, so powers of 2, 2, 4, 8, 16, 32, 64, 128, 256, 512, 512, 1000, 512, 1024, and then 2048. So, 1086 byte will fit the 2048. So, subtract. So, internal fragmentation of 2048 minus 1086. So, we have 962 bytes. So worst case fragmentation is equal to one frame, which is almost one frame, one byte. So on average, fragmentation is equal to one half frame size. So our small frames sizes desirable rather. So but each page table entry takes memory to track. So page size is growing over time. So as much as possible, it is very convenient to have frame sizes that are big enough to accommodate other processes with big sizes for pages. So we have this, for example, we have Solaris supports. So let's go back with our presentation. Solaris supports two page sizes, which is 8 kilobyte and 4 megabyte page sizes. Okay, next is we have free frames. So of course, so there are also free frames. So we have the free frame list. For example, we have the 14, 13, 18, 20, and 15. So this is our frame list. And then we have this in the backing store, the pages, page 0, 1, 2, 3. And then, of course, this is the backing store for new process. And then what happens here, since we have free frame list, then we need frames for these pages. So these pages will be assigned to, for example, page 0 will assign to frame number 14. So that's why 0 is in frame number 14. So page 0 is frame number 14. And then page 1 is in frame number 13. So that's why page 1 is here. And then um, we have the page 2 will be located in frame number 18. And then last but not the least, we have the page 3 will be located in frame number 20. So this is before allocation and after allocation. So the allocation of pages will be these pages will use the frames that are free, or these are actually no process that's still been using these frames. Okay, next is we have implementation of page table. So page table is kept in main memory. So we have the so-called page table register, or PTBR, points to the page table. We also have the page table length register, or PTLR, indicates size of the page table. So base and length register. So in this scheme, every data or instruction access requires two memory accesses. So one for the page table and one for the data or instruction. So that's why two memory accesses. So the two memory access problem can be solved by the use of special fast lookup hardware cache called the translation look aside buffers, or TLBs, are also called associative memory. So what is TLB, or translation look aside buffer? So some TLBs store address space identifiers in each TLB entry. So this uniquely identifies each process to provide address space protection for that process. So that's why it's called address space identifiers. Otherwise, need to flush at every context switch. So flush means erase. So typically, TLB's sizes are small, from 64 to 1024 entries. So on a TLB miss, so we have the TLB hit. If there's a TLB hit, meaning that the address is there on the TLB, but if not, so it's a TLB miss. So value is loaded into the TLB for faster access time. So replacement policies must be considered, and then some entries can be wired down for permanent fast access. Wired down meaning the values will not change inside the TLB. So hardware, so associative memory uses parallel search. So we have page number and frame number. So address translation is also the page number and offset. So if P is in associative register, get frame number out. Otherwise, get frame number from page table in memory. So this is what happens for paging hardware with TLB. So instead of only a page table, we have TLB or translation look aside buffer. So again, our CPU produces logical address P and D with page number and page offset. And then this page number has a corresponding value for the TLB, which is composed of page number and frame number. So if the value is inside this TLB, then we have a TLB hit. So this will be loaded faster in the physical address. So what if the value is not here, so it's not in the TLB, so it's a TLB miss. So this the page number will be acquired from the page table, and this will be loaded here. And then after the physical address, so you have to add for the physical address the offset, and combining of course again the value, it's either from the TLB or from the page table. From the TLB, if the value is already in the TLB, in the if it is located in the page table, meaning the value is not yet in the TLB. So this will be combined so that this will be the address in the physical memory. So we also have this so-called effective access time or EAT. So we have hit ratio, percentage of times that a page number is found in the TLB. So this is actually desirable that the page number is already found in the TLB. So it will the execution will be faster. But if the page number is not found in the TLB, then it will be acquired from the page table. So an 80% hit ratio means that we find the desired page number in the TLB 80% of the time. So we have this example. So suppose that 10 nanoseconds to access memory. So if we find the desired page in TLB, then a map memory access takes 10 nanoseconds. So otherwise, so what if it's a TLB miss? We need 2 memory access, so it is 20 nanoseconds. So why is it 2 memory access? As we can remember, let's go back with the figure. So for the page number, it will always search first for inside the TLB. If the page number is already available, so that will be a TLB hit, so it's only one access. But once the page number is not available in TLB, so first it is accessed in TLB, and then it will also access the page table. So that's why the memory access is times 2, because you need to look first at the TLB, and if it's a miss, then you need to look at the page table. So for TLB miss, it will be 20 nanoseconds, 10 times 2. So what is the effective access time? So the effective access time is what? So 80%, so we have 0.80, then the access is 10 nanoseconds. So this will be for the TLB hit, and then this part is the TLB miss. So we have 100 minus 80, which is 20%, or 0.20 times 20, since if it's a TLB miss, it accesses the memory 2 times. So that's why 2 times 10, so we have 20 is equal to 12 nanoseconds. So we can also again have our calculator. Okay, so again our calculator here. So just to make sure, 0.80 times 10. Okay, so we have 8, and then 0.2 times 20, 4 plus 8, so of course we have 12, implying 20% slowdown in access time. So what is this 20%? Okay, since our access time to access the memory is 10 nanoseconds, then we have 12 nanoseconds, meaning it adds 2 seconds to access memory because of the TLB miss. So what we're going to do here is 12 minus 10 is equal to 2. And then this 2 will be divided by 10 because that is the time it takes to access the memory, the ideal. Okay, so 2 divided by 10 is equal 0.2, or if you're going to do it in a percentage, so it means 20. That is why there is a 20% slowdown in access time. So that 2 seconds here is the 20% slowdown in access time. Okay, so what if we have consider a more realistic hit ratio of 99%? So we have 99, so it means that our TLB hit ratio here is 0.99 since 99%. So our effective access time, of course, again, so we have 0.99 plus, or rather, okay, let's repeat it again, 0.99 times 10, so we have 9.9, and of course, this is the TLB hit. The TLB miss is, of course, 100 minus 99, which is 1, which is 1%, so that's why 0.01 times, again, because 20, because of this is a TLB miss, it needs to access memory twice. So times 20 is equals to 0.2 plus 9.9 for the TLB hit. Okay, we have 10.1 nanoseconds. So, implying only 1% slowdown in access time. So, how do we get again this percentage? With the same with here, with the 20%, is we have 10.1. Of course, again, our access time is 10 nanoseconds as indicated in the problem, minus 10. So, we have 0.1. Then again, divided by 10 nanoseconds. So, we have 0.01. So, if we're going to convert it into percentage, so this will be the 1% slowdown in access time. So, I hope you understand how to compute the effective access time when using translation look-aside buffer. Okay, so let's continue. Next is we have memory protection. So memory protection implemented by associating protection bit with each frame to indicate if read-only or read-write access is allowed. Can also add more bits to indicate page execute only and so on. So we have the valid invalid bit attached to each entry in the page table. So valid indicates that the associated page is in the process logical address space and is thus a legal page. And then we also have invalid, indicates that the page is not in the process logical address space. Or we could also use the page table length register, or the PTLR. So any violations result in a trap to the kernel. So we can see, for example, how does the valid or invalid bit in a page table is applied. So for we have 1, 2, 3, 4, 5, 6. So we have 6 pages for logical memory or address. So this 6 pages is loaded here. So 0 will be located in page 2. So page 1 will be located in page 3. So page, okay, let's return again. Okay. Okay, so again, page 0 will be located in page 2, or rather frame number 2 of the physical memory. Then page 1 will be in frame number 3, so that's why it's in frame number 3. And then page 2 will be in frame number 4. And then we have page 3 will be in frame number 7. And then page 4 will be in frame number 8. And we have page 5 will be in frame number 9. Okay, so this 6 pages, so by using valid or invalid bit, they're all V. They're all valid because they're all existing as logical address. So we have 6 and 7, since it does not exist here, the logical address, so the valid invalid bit here is we have I. So as you can remember here, valid if the associated page is in the process logical address space. So invalid, since we do not have for page 6 or page 7, we only have 6 pages, and here is we have 8 since we don't have for the 7th and 8th page for it. So that's why these are all invalid, these two. Okay, next is we have shared pages. So we have shared code. One copy of read-only or reentrant code shared among processes such as text editors, compilers, and Windows system. What is reentrant? So reentrant is a non-modifying code. It never changes during execution. So similar to multiple threads sharing the same process space. So this is useful, the shared code, for inter-process communication if sharing of read-write pages is allowed. Then we also have the private code and data. So each process keeps a separate copy of the code and data. The pages for the private code and data can appear anywhere in the logical address space. So we have shared pages example here. So we have this for process P sub 1 and process P sub 3. So we also have process P sub 2, and then they have their corresponding page table for P sub 1, P sub 3, and P sub 2. But since they are using the same libraries and page table, so it should be located all at the same location. That's the mechanism of shared pages. So that because they are sharing these pages, the address in the physical memory must all be the same. Okay, next is we have the structure of the page table. So memory structures for paging can get huge using straightforward methods. So consider a 32-bit logical address space as on modern computers. So page size of 4 kilobytes 2 raised to 12. So for this, page table would have 1 million entries. So we have 2 raised to 32 for the page number and 2 raised to 12 for the page offset. So if each entry is 4 bytes, each process 4 megabytes of physical address space for the page table alone. So don't want to allocate that contiguously in main memory because I think main memory will not be enough for other processes. So one simple solution is to divide the page table into smaller units. So how we're going to divide that is by using hierarchical paging, hashed page tables, and inverted page tables. So first is we have hierarchical page tables. So break up the logical address space into multiple page tables. So a simple technique is a two-level page table. So we have this one. So this table, outer page table, is divided. So we have 3 here for an example. And then this will also be divided. So this is a two-level page table. So this one will have its own address, physical address in memory. So we then page the page table. So that's the hierarchical page table. This is a two-level page table. So two-level paging example. So a logical address on a 32-bit machine with 1 kilobyte page size is divided into. Okay, it can be a page consisting of 22 bits and a page offset consisting of 10 bits. So 22 plus 10 is equal to 32. So since the page table is page, the page number is further divided into. So we have the 22 here is divided with 10-bit page number, and we have a 12-bit page offset. So the logical address is as follows. For page number, we have P sub 1 and then P sub 2, and then we have the page offset of 12. So 10 plus 10 is equals to 20 plus 12 is equals to 32. So where P sub I is an index into the outer page table, P sub 1, and then P sub 2 is the displacement within the page of the inner page table. So this is known as the forward mapped page table. So this is the addressing for two-level paging. So example, for the address translation scheme, so we have P sub 1, P sub 2 as the page number, and then D is for the page offset. So P sub 1 is said that it will access the outer page table. So after accessing the outer page table, then use P sub 2 to get the page of the page table, and then we are going to add the offset. Okay, next is we have 64-bit logical address space. So even two-level paging scheme is not sufficient. Of course, so if page size is 4 kilobytes or 2 raised to 12, then page table has 2 raised to 52 entries. It's actually too much. So if two-level scheme, inner page tables could be 2 raised to 10 4-byte entries. So the address would look like it's still actually big. For the outer page for P sub 1 is 42, inner page is 10, and then offset is 12. So 42 plus 10, we have 52 plus 12 is we have 64. So the outer page table has 2 raised to 42 entries or 2 raised to 44 bytes. It's too big. So one solution is to add a second outer page table. But in the following example, the second outer page table is still 2 raised to 34 bytes in size and possibly for memory access to get one physical memory location. So this is the example as it is said is we have outer page is 42, then 10, and then 12 for 64-bit. So create another for the second outer page table, but it's still big. For P sub 1, we have 32. And then outer and inner page is just the same as 10. And then the offset is 12. So this will also be equivalent to 64-bit. So to solve that problem, so we are going to use hashed page tables. So common in address spaces greater than 32 bits. So the virtual page number is hashed into a page table. So this page table contains a chain of elements hashing to the same location. So each element contains number 1, the virtual page number 2, the value of the mapped page frame, and number 3, a pointer to the next element. So virtual page numbers are compared in this chain searching for a match. If a match is found, the corresponding physical frame is extracted. So variation for 64-bit addresses is clustered page tables. So similar to the hashed, but each entry refers to several pages such as 16 rather than 1. And then specially useful for sparse address spaces, or sparse meaning distributed address spaces, where memory references are non-contiguous and scattered. So this is an example of a hashed page table, the illustration how it is done. If we have a logical address for the page number, it will access it has the hash function, and it will access the hash table. So the hash table consists of values in linked list, and if the value is found, then it will be extracted from the hash table, and then the page offset will be combined to get the physical address corresponds to the physical memory. Okay, next is we have another one aside from hashed page table is we have the inverted page table. Rather than each process having a page table and keeping track of all possible logical pages, track all physical pages. So one entry for each real page of memory. So entry consists of the virtual address of the page stored in that real memory location with information about the process that owns that page. So the advantage is it decreases memory needed to store each page table, but increases time needed to search the table when a page reference occurs. So use hash table to limit the search to one or at most a few page table entries. So TLBs can accelerate the access. So the question here now is, but how to implement shared memory? So the solution here is one mapping of a virtual address to the shared physical address. So this is the illustration of the inverted page table architecture. So the CPU, the logical address. So we have the PID, and then we have also the page number and the offset. So it will search the page table with the PID and the page number. So if the value is located, so it will be extracted, and then the offset, page offset will be added. So it will produce the physical address corresponds to the actual address in the physical memory. Okay, next is we have Oracle Spark Solaris. So we have an example of an operating system here. How does the memory access or paging is happening in this operating system? So consider modern 64-bit operating system example with tightly integrated hardware. So goals are efficiency and low overhead. So this is based on hashing but more complex because it uses two hash tables. So one kernel and one for all user processes. Each maps memory addresses from virtual to physical memory. Each entry represents a contiguous area of mapped virtual memory. So more efficient than having a separate hash table entry for each page. And then each entry has base address and span, or this indicates the number of pages the entry represents. So for Oracle Spark Solaris, it has a TLB that holds translation table entries or TTEs for fast hardware lookups. So a cache of TTEs resigned in a translation storage buffer or TSB includes an entry per recently accessed page. And then virtual address reference causes TLB search. If it's a TLB miss, so hardware walks the in-memory TSB looking for the TTE corresponding to the address. If match is found, the CPU copies the TSB entry into the TLB and translation completes. If no match is found, kernel interrupted to search the hash table. The kernel then creates a TTE from the appropriate hash table and stores it in the TSB. Interrupt handler returns control to the MMU or the memory management unit, which completes the address translation. So that is for Oracle Spark Solaris. Okay, next is we have swapping. So a process can be swapped temporarily out of memory to a backing store and then brought back into memory for continued execution. So backing store here is, example, a hard drive. So total physical memory space of processes can exceed physical memory. So that's why it needs to be swapped, because sometimes the physical memory space needed by the processes is bigger than the physical memory itself. So backing store, as I've said, can be a hard drive. So it's a fast disk large enough to accommodate copies of all memory images for all users, must provide direct access to these memory images. We have the roll out, roll in. So this is also a swapping variant used for priority-based scheduling algorithms. Lower priority process is swapped out, so higher priority process can be loaded and executed. So that is why called the low priority process will be rolled out while the higher priority process will be rolled in. So that is the term of the roll out, roll in swapping variant. So major part of swap time is transfer time. Total transfer time is directly proportional to the amount of memory swap. Of course, if the physical memory space of the process is large, so the transfer time is slower. Just like, for example, in a real world scenario, for example, if you're transferring one object from one location to another, if the object is light, you can transfer it faster because it's light. But what if you're going to transfer, for example, a refrigerator, which is very heavy? Even if you're going to do it by hand, or of course, it will take time for you to transfer it from one location to another. So it's also with in the computer system in main memory. So the total transfer time is always directly proportional to the amount of memory swapped. And then system maintains a ready queue of ready-to-run processes which have memory images on disk. Okay, so does the swapped out process need to swap back into the same physical addresses? Okay, the answer to that question, it depends on the address binding method. So plus consider pending IO to or from process memory space. So modified versions of swapping are found in many systems such as Unix, Linux, and Windows. So swapping actually is normally disabled for these systems. It will only start if more than threshold amount of memory is allocated, and then it will be disabled if the memory space, the physical memory is enough, then swapping is disabled. Yes, disabled. But if it exceeds the needed memory space, then it will be enabled. So it will be disabled again once memory demand reduced below threshold. So this is the schematic view of swapping. So again, this is our main memory, a fixed logical fixed address for operating system, and then we have the user space. So for example, process P sub 1 is inside the main memory, and process P sub 2 is to be swapped in. So for example, for a clear example, P sub 1 is you are you have opened the internet browser, and then process P sub 2 is you're going to type a Word document, for example. So while you're searching the internet browser, the internet, so process P sub 1 is in memory. So then after you've searched the what you needed in the internet, then you decided to use the Word document. For example, you have a project that you are doing, you're researching for an article. So, from process P sub 1 in which you are doing your internet browsing, and then when you use your Word document, this what happens. So, process P sub 1, which is the internet browser, will be swapped out if the main memory space is not enough for the both of them. But if of course if it's enough, there's no swapping that will happen, as indicated in the previous slide, that this is normally disabled. It will only be enabled if the space will not accommodate the process anymore. So again, let's go back with our example. Once you've using your Word document, so since you're not using the internet browser for researching, so this will be swapped out, process P sub 1. And then your word processor, since you're already typing or you're doing your project, so this will be swapped in. So that is the schematic view of swapping. An example. Okay, next is we have the context switch time, including swapping. So if next processes to be put on CPU is not in memory, need to swap out a process and swap in target process. So context switch time can then be very high. So we have 100 megabyte process swapping to hard disk with transfer rate of 50 megabytes per second. So swap out time is 2000 milliseconds. Okay, and then we have plus swap in of same size process. So total context switch swapping component of 4000 milliseconds. Okay, then can reduce if reduce size of memory swap by knowing how much memory really is being used. So we have system calls to inform OS of memory used via request underscore memory function and release underscore memory function. Okay. Okay, other constraints as well on swapping. So pending input output can swap out as IO would occur to wrong process. So always transfer IO to kernel space, then to IO device. So known as double buffering adds overhead. So double buffering is the copying of data twice, such as from a device to the kernel and then from the kernel to a process address space, or the use of two buffers to decouple producers and consumers. So standard swapping not used in modern operating system but modified version common. So as it is said, swap only when free memory extremely low. And then, is there a swapping on mobile systems in our smartphones or in our cell phones? So, swapping is typically not supported. So, because it is flash memory based and it has only a small amount of space, limited number of write cycles. So, poor throughput between flash memory and CPU on mobile platform. So, instead, use other methods to free memory if low for iOS. iOS asks apps to voluntarily relinquish allocated memory, read only data thrown out and reloaded from flash if needed. Failure to free can result in termination. So while Android terminates apps if low free memory, but first writes application state to flash for fast restart. So both OSs, iOS and Android supports paging as discussed. So we have the swapping with paging. So, for example, process A has B, C, and D page. So, it's not really the process but the page. So, this will be paged out and it will be stored in backing store. And then the corresponding, since this is 3, that is needed by process B. So, it will be paged in the main memory. So next is we have example, the Intel 32 and 64-bit architectures. So these are the dominant industry chips of Intel, and Pentium CPUs are 32-bit and called IA32 architecture. So currently, Intel CPUs are 64-bit and called IA64 architecture. So many variations in the chips cover the main ideas here. So for the Intel IA32 architecture, supports both segmentation and segmentation with paging. Each segment can be 4 gigabyte, up to 16 kilobyte segments per process, and these are divided into two partitions. So first partition of up to 8 kilobyte segments are private to process, and it is kept in local descriptor table or the LDT. And then we also have the second partition up to 8 kilobyte segments shared among all processes. Since this is shared, or rather all shared, these are kept in the global descriptor table or the GDT. So CPU generates local logical address rather. So selector given to segmentation unit. So which produces linear addresses. So for here we have S. So S is segment number. So G, it's either a local from the location of a local descriptor table or a global descriptor table. And then P is for protection. So linear address given to paging unit, which generates physical address in main memory. So paging units form equivalent of main memory management unit, and page sizes can be 4 kilobytes or 4 megabytes. So IA32, so the address is a 16-bit linear address. Okay, next is we have logical to physical address translation in IA32. So for the CPU, it will derive the logical address and then it will undergo process in the segmentation unit, and then it will produce the linear address, and then it will undergo under the paging unit and it will produce the physical address, and it will be the corresponding address in the physical memory. Okay, next is we have the Intel IA32 segmentation. So our logical address is composed of selector and offset. So this selector points to the description table and the actual location of the segment descriptor, and then this will be combined into the offset, and then the offset is a 32-bit linear address. Okay, there we have the Intel IA32 paging architecture. So we have so So we have the 10 higher order bits references an entry in the outermost page table, which IA32 terms the page directory. So we have this one. So From 0 to 11, this is the offset. Then from 12 to 21, it will points to the page table. And 22 to 31, this is the 10 high order bit references. Uh, an entry in the outermost page table. So this is the one. And then our CR3 register points to the page directory for the current process. And then the page directory points to the inner page table. This is the inner page table. That is what? Indexed by the contents of the innermost 10 bits in the linear address. So this is the 10 bits. Okay. Then finally, the low order bit 0 to 11, which is the offset. This refers, of course, to the 4 kilobyte page pointed to the page table. And also, aside from the page directory pointing to the page table, it also points to the 4 MB page. Okay. So next is we have the Intel IA32 page address extensions. So 32-bit address limits led Intel to create the page address extension or the PAE. Okay. Allowing 32-bit apps access to more than 4 gigabyte of memory space because for 32 bits, it can only access 4 gigabyte of memory space. But because of page address extension, it increases its limit that it can access more than 4 gigabyte of memory space. So paging went to a 3-level scheme. So top 2 bits refer to a page directory pointer table, and then page directory and page table entries move to 64 bits in size. And the net effect is increasing address space to 36 bits as to 64 gigabits of physical memory. So from 32, it become 36, and then it can access an additional or a bigger size, which is 64 bits of physical memory compared to 4 gigabytes rather of memory space. So for, again, it's a 32 bits, so 0 to 11 is the offset, 12 to 20 is the page table, and 21 to 30 is the page directory, and then we have 1 byte here for the page directory pointer table. So this also illustrates a PAE system with 4 kilobyte pages. So also PAE supports 2 megabyte pages. Okay, so again, we have the CR3 register points to the page directory table, and then this points to the page directory, and then this address is for the page directory, and then page directory points to the page table. So this one, this address, this bits is for the page table, and of course, we have a 4 kilobyte page, combining for the offset and the values of the page directory and the values in the page table. Okay, next is we have the Intel x86-64. So current generation Intel x86 architecture. So 64 bits is ginormous, greater than 16 exabytes. So in practice, only implement 48-bit addressing. So page sizes can be of 4 kilobytes, 2 megabytes, and 1 gigabyte because it's too big. And then it has a four levels of paging hierarchy. Can also use PAE, so virtual addresses are 48 bits and physical addresses are 52 bits. So again, this is the composition of its 64-bit address. So we have offset for 0 to 11, 12 to 20 bits is the page table, 21 to 29 is the page directory, 30 to 38 is the page directory pointer table, and 39 to 47 is we have the page map level 4. And of course, it is said that in practice only implements 48-bit addressing, so 48 to 63 is unused. Okay, another example is we have the ARM architecture. So dominant mobile platform chip, which is used by Apple iOS and Google Android devices, for example. It is modern, energy efficient 32-bit CPU. It uses 4 kilobyte and 16 kilobyte pages. And then we also have 1 megabyte and 16 megabyte pages for sections. So, one level paging for sections, two level for smaller pages. So, it has two levels of TLBs. So, outer level has two micro TLBs, one data and one instruction. And then inner is a single main TLB. And then first inner is checked. On miss, outers are checked. And on miss, on page table walk performed by CPU. So, it's a 32-bit. So, it is composed of the offset inner page and outer page table. It is said here that for it has two levels of TLBs, micro TLBs, and then for this one, and then we also have an inner single main TLB. Okay, and then this will be composed for a 14 kilobit or 16 kilobit page, or 1 megabyte or 16 megabyte for section. Okay, so this is the end for chapter 9, all about main memory. So I hope that you learned something about the different mechanisms of the address spaces, of converting logical address space to physical address space of main memory, and the different mechanisms and implementation by using page tables, and of course the so-called paging. So if you do have any questions, so please feel free to comment below, and please do not forget to subscribe to my channel. So again, thank you very much for listening. I hope that you've learned something again, and then join me in my next lectures. So thank you very much and good day.